Welcome to the Watchdog Timer. Most CPUs are equipped with a Watchdog Timer that resets the CPU or generates an interrupt if processing comes to a standstill for whatever reason. This feature ensures system reliability in industrial, standalone, or unmanned environments. To enable the Watchdog Timer, a program must read a specific I/O port address at regular intervals. The first time the program reads the port, it enables the Watchdog Timer. After that, the program must read the port at an interval shorter than the timer's preset interval. If CPU processing comes to a standstill because of EMI or a software bug, the program's reading of the specific I/O port will not occur. The timer will then automatically reset the CPU or invoke an IRQ, and data processing will continue once again. In other words, your program should have instructions that will refresh the timer within the timer's preset interval. Otherwise, the Watchdog Timer will activate and reset the CPU or generate an interrupt. The Watchdog Timer of a 68AC11 CPU is the COP system, and COP stands for Computer Operating Properly. When the COP is enabled and if the software is not able to keep the free-running Watchdog Timer from timing out, the Watchdog Timer generates the COP failure interrupt. The interrupt vector assignment for the COP failure interrupt is FFFA and FFFB. The state of the no COP bit in the config register determines whether the COP system is enabled or disabled. To change the enable status of the COP system, change the contents of the config register and then perform a reset. To enable the COP, the no COP bit needs to be set to a 0. To disable the COP, the no COP bit needs to be set to a 1. In the special test and bootstrap operating modes, the COP system is initially inhibited by the disable resets control bit in the test1 register. The DISR bit can subsequently be written to 0 to enable COP resets. The option register is used to set the timeout period for the COP timer. The COP timer rate control bits CR1 and 0 in the option register determine the COP timeout period. The system E-clock is divided by 2 to the 15th and then further scaled by a factor shown in the following table. After reset, these bits are 0, which selects the fastest timeout period. In normal operating modes, these bits can be written only once within 64 bus cycles after reset. To arm and reset the COP timer, a 55 hex value must be written to the COP reset registered, followed by an AA hex. To use the COP system, enable the COP by writing a 0 to the no COP bit of the config register. The value to write to the config register is FB hex. In JBug 11, enter config FB at the command prompt. The enabling of the COP can also be done in the program itself. Note, allow the writing of the config register by writing a 00 hex or a 0F hex to the bit protection register. Then, in your program, configure the COP timer rate control bits within the first 64 bus cycles out of reset. This applies to single chip and expanded modes only. And then finally, write a 55 hex to the COP reset and then a AA hex to the COP reset. This sequence must be done within the allotted time interval to avoid the triggering of the COP failure interrupt. The following program demonstrates the COP system. This program is meant to run in single chip mode. Use JBug 11 to configure the config register. First run the program with the COP disabled and then with the COP enabled. Explain why the same program reacted differently. LEDs are connected to PB0, PB1, PB2, and PB3. Let's analyze the code. At the very top of the program, we have our origin at F800. Then we initialize a stack. This is because we're going to be running this in single chip mode. The next thing, we loaded accumulator A with a 1-3, and then we wrote that or stored it at the option register. So here we have the option register and all the bits that are inside of it. So by sending a 1-3, we end up with a 0, 0, 0, 1. So we're not changing anything in those bits. And then a 3 is a 0, 0, 1, 1. So it sets our CR1 high and our CR0 high as well. And because we have a 1, 1 in the CRs, we're going to be working with this row. And since our CPU has an 8 megahertz crystal, that means that we are having an interval of 1.049 seconds. What this means is that we need to write to the Watchdog timer within that allotted amount of time. If not, it's going to time out and then it's going to cause the CPU to reset. Looking back at the program, then we go to JSR cop. So this is a subroutine. What does a subroutine do? If we look at the cop subroutine towards the bottom, we see that we're writing a 55 hex and then an AA to the cop reset register. The first time that we do that, that enables the Watchdog timer. So now the Watchdog timer is turned on. Then after that, we go back up to the main program where we are loading a 0, 1, and then we're storing it at port B. So therefore LED 0 is now on. Then we go to a delay. The delay, which is here, is going to have a time of about 0.2 seconds. About 0.2 seconds. Now after that, we go to a next JSR cop, and again, we need to keep writing to the Watchdog timer within that 1.049 seconds, because if not, it's going to time out and cause the CPU to reset. But we're inside of that allotted time, so the CPU will not reset. So it just continues on executing our code. So it goes to the JSR cop, it resets it, it's done within the allotted time, so everything is fine. So it goes back to the next line of instruction, which is to load accumulator A with a 0, 2 and store it at port B. Then it goes to a delay. So now LED 1 is on. And if we were to put some LEDs over here, something like this, there's 4 of them. So this is LED 0, this is LED 1, LED 2, and LED 3. So now LED 1 is on, and it stays on for about 0.2 seconds. Then we go back to doing a write to the cop. So therefore we reset the cop, and then we go on with our code because it was still done within the allotted 1.049 seconds. And this next write to port B is going to turn on LED 2. Then it goes to a JSR delay. This again will take up about 0.2 seconds, but it's still not past the 1.049 seconds. So again, it just continues with the next instruction. This instruction is to do a 55 writing and then an AA writing to the cop reset register. And so again, it's done within the 0.049 seconds, so everything is fine. Then finally, it goes down a bit further, and this is where we're turning on our last LED, which is LED 0. So where it stores it here, this is turning on LED 3. This one here is LED 2. This one here is LED 1. And this storing over here is LED 0. Now finally, it goes to load accumulator A with a 0, 0, stores it at port B. Then it goes to JSR cop. It does the writing of a 55 hex and an A hex. And then, now when it does that, it resets that timer. So therefore, it starts back at 0. But then we go into a branch over, and right here is where it gets stuck, in a sense, in an endless loop. Now, because we're not able to write to the Watchdog timer, because we're not able to send that 55 and that AA to the cop reset register, because we're stuck in an endless loop, then the timing constraint, which is 1.049 seconds, is going to get passed. We're going to go above that. In other words, the Watchdog timer is going to get timed out. So it's going to time out because we were not able to reset the cop reset register. So therefore, it times out. And what is to happen next? Well, because the Watchdog timer timed out, then it causes a reset of the CPU. And when it causes a reset of the CPU, what happens then? Well, once it resets the CPU, one thing to be aware of is that it's going to look at the cop failure interrupt vector assignment, which is right here. That's where it's going to look at. And because I configured it with an FCB of F800, that means when it goes and looks at FFFA and FFFB, it's going to pull the F8 and the 00. It's going to put it together as an address, and it's going to go to that address and execute code, which happens to be what? Well, the start of the program up there again. So what is happening then, the overall program, it is flashing LED 0, then LED 1, then LED 2, then LED 3, and then all the LEDs are off at this point, and then it waits about 1.049 seconds. Well, actually, it does, right? It waits 1.049 seconds because that's how long it takes the Watchdog timer to time out. And then when that happens, it goes to the cop failure interrupt vector assignment, grabs that F800, and knows that it's supposed to go to that address, which causes it to do what? Well, causes it again to flash LED 0, then LED 1, then LED 2, then LED 3, and then everything goes blank, and then about a second afterwards, it flashes them all over again. And that's showing you that the Watchdog timer is operating. And this concludes the lab on the Watchdog timer.